Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Chance Millett-Bangs from the Business Review, and I will be your host. It is our pleasure to have VTT with us today, who will be discussing Microbes, the new designers of food structure and taste. Today's guest speakers are Aya Leitala, Principal Investigator at VTT, and Nesli Souza, Senior Scientist at VTT. We also have Rika Juvonen, Senior Scientist of Process Microbiology and Safety at VTT, who will be moderating today's Q&A session. I'd like to welcome you to our new webinar platform. You'll notice that this webinar is browser-based, so if you disconnect, please click the link that you received via email to rejoin. In order to ask questions, you can send them in via the Q&A widget at the bottom of your screen, or use the questions box at the top left-hand corner of your screen. We will allocate around 10 to 15 minutes at the end of the session to address any questions or thoughts that you may have. You may also use the Twitter widget to tweet about today's webinar throughout the presentation. Please use the help widget if you require any more assistance. So without further ado, please allow me to welcome Aya. Aya, over to you.
Thank you, Chance, for your kind introduction. Good morning, good afternoon, everybody, and welcome to this webinar. I am Aya Leitala, and I will be the first speaker today. I have also a pleasure to introduce my good colleagues Nesli and Rika, who will also introduce you some of the latest research results and also answer your questions. But let me start this presentation with a very short introduction to VTT. VTT Technical Research Centre of Finland is the biggest applied research organization in Northern Europe. We are doing applied research and provide technology solutions and innovation services for companies as well as for public sector. Our research is driven by three key areas: the digital world, manufacturing industry, and then natural resources. We are a globally network organization, and our turnover is around 300 million euros, and the staff number is nearly 3,000 people. I could highlight here that nearly half of the Finnish demanding innovations include our expertise, and approximately 36 of all Finnish innovations have benefited from our expertise. Today we will discuss how microbes can be applied in bioprocessing of food. I will first give you a short introduction to the benefits of microbial food cultures. Then we will focus on three different case examples in which we have applied microbial technology. First, I will discuss how to replace food additives with microbes, and then we will show you how food ingredients can be modified with fermentation in order to increase dietary fibre. You will also see our recent studies on development of new protein-rich products with the help of microbes. Fermented products such as bread, cheese, beer and wine have been prepared and consumed for thousands of years. Different cultures in various parts of the world are using fermentation as a tool to improve taste, nutritional and technological quality of food products. For sure we can say that food fermentation with the help of microbes is one of the oldest food processing technologies. Fermented foods and beverages have huge economic impact and cultural impact in all the continents. Food and Agriculture Organization of the United Nations has been estimated that approximately 1/3 of all food products currently being consumed are actually fermented. Fermented products are also attractive to young consumers, also to Generation Z, or in other words, individuals born during this millennium. It has been said that this generation has collective attitude towards food simplicity and health. They tend to seek unique tastes and foods with authentic stories. And in the group of fermented beverages and foods, we can find several fantastic stories. microbes really can give special characteristics to the product. Microbes are often an integral part of the raw materials used in food processing. The figure left-hand side illustrates you the microbial community naturally present in cereals, and we can see a lot of different microbial cells. Thus, we can induce fermentation process simply by adding water to food ingredients. Early fermentation processes relied on the mixtures of natural wild yeast and bacteria, and in several cases nobody had any idea what was actually happening when they were preparing the product by fermentation. Nowadays, majority of industrial food fermentation have been moved from spontaneous process into controlled production concepts. By selectively modifying the microbial community, we can ensure controlled food and beverage production and consistent quality and produce products with desired characteristics. Modern industrial microbiology defines fermentation as a process of biotransformation with microbes and their enzymes. The process can be based in the anaerobic metabolisms of organic substrates, as in the classical sense. Nowadays also aerobic microbial processing is included in the concept of fermented foods. Microbes are mainly added in a purified and enriched form, and the nature of organisms will determine the impact of the final product quality. Microbial food cultures can be used at one or more stages in the food production process to obtain specific functional, sensorial, nutritional, and stability properties. Microbial food cultures include bacteria, yeast, and molds. They can be used as single cultures or multifunctional mixtures consisting of different bacteria and fungi. Perhaps the most widespread examples are the use of lactic acid bacteria and Saccharomyces, brewers and bakers' yeast. They have great industrial importance in the production of fermented foods and beverages. So how could microbial food cultures meet the top future trends in food and ingredient industry? We have tried to summarize some of our ideas in this slide. We picked up 6 of the main future trends to the list on the left-hand side. Consumers have a preference for traditional and artisan products with natural image. Products should preferably have a long product shelf life. Then consumers' health awareness is strongly increasing. We also need to fulfill the protein cap in the future. Big theme is also sustainable use of raw materials and a trend towards zero waste. As we shortly discussed, microbial food cultures have a long history of safe use, and for sure we can say that fermented products are traditional. Several microbes are applied as natural preservatives in order to lower the pH and to produce antimicrobial compounds, thereby increasing safety and shelf life. In addition to antimicrobial compounds, microbes can produce other valuable compounds which can help to reduce the use of food additives. And we will give you one example in this presentation. Consumer health awareness continues to grow with the aging populations and increased risk for lifestyle diseases. Fermentation is a process to increase nutritional value of raw materials, as you will also learn in our case examples. We need an adequate supply of protein in the future. Microbes can help in this business. Microbes themselves are a natural source for proteins. In addition, they can increase the availability of essential proteins and peptides by releasing and modifying proteins from complex material. And we will give you an example of this. Sustainable food production and consumption are important when considering future food policy. Microbes open up several opportunities to valorize side streams coming from the agri-food sector. So, microbes can be an answer to many future demands in food production. So let's go now to the case studies. Microbial food fermentation provide a means to produce additive-free products with natural image. I will give you an example of wheat bread baking. Wheat bread is the main bread type consumed in the world. It is well known that clean label bakery products have rather limited shelf life without additives and enzymes. Baking industry has expressed a need for multifunctional microbial cultures that could be used to design flavor and also to improve technological properties. Traditional sourdough technology is a natural alternative to improve shelf life, aroma, and nutritional value of baked products. In sourdough process, flour is fermented with yeast and lactic bacteria. Sourdough microbes then give flavor and also increases volume of baked products due to gas formation. Unfortunate use of traditional sourdough in wheat bread baking is often limited due to negative impact of high acidity on flavor and bread structure. Lactic bacteria that are producing exocellular polysaccharides, EPS, provide an option to produce new clean label products. Lactic bacteria can synthesize a wide variety of EPS with different functionalities and structures. EPS are effective at low concentration and exhibit a positive effect on the texture, mouthfeel, taste perception and stability of fermented products. Dextran is perhaps one of the well-known exopolysaccharides produced by lactic bacteria and has great potential as a bread improver in the baking industry. In situ exopolysaccharide production by fermentation technology is a natural tool to replace food additives such as emulsifiers, thickeners, and preservatives, as well as anti-staling enzymes in the bakery products. In baking applications, dextran can bind high amounts of water, thus lead to an improved freshness of the end product. Furthermore, dextran improves dough stability and gas retention through a specific structure buildup of dextran and gluten network, as can be seen from these figures on the right-hand side. In addition, EPS have potential to improve gut health. Thus, microbial EPS-enriched products could, for instance, provide a new source of prebiotic oligosaccharides. We can say that EPS production by fermentation is a natural technology for introducing hydrocolloids into food. By strain selection and process optimization, the technology can be tailored to produce EPS with desired characteristics, not only in the bakery products, but also in other food matrices. We have been able to produce exopolysaccharide containing sourdough-based products with mild acidity. In normal wheat bread baking, the addition levels of sourdoughs are between 10 to 20%, since intensive acidification is known to negatively influence bread volume, crumb hardness, and firming. Strong acidity is not accepted by most of the consumers. Here we use Lactobacillus brevis as a control sourdough strain, and as can be seen from the third column, it was strongly acidifying strain. High acid production led to low pH of bread. We were able to show that with Vaisella strain, it was possible to produce sourdough bread with mild acidity. Furthermore, it nicely produced dextran. The dextran levels in Vaisella fermentation after 17 hours fermentation was over 1.5%. We have also been able to increase the level of sourdough addition with EPS-producing lactic bacteria. We could use over 40% of sourdough addition, thus obtaining higher concentration of dextran in the final bread, though without negative impact on the flavor and texture of bread. This figure illustrates by using dextran-positive vegetable sourdough in wheat baking, we could improve softness of fresh bread by about 20% over the control breads and also those containing EPS-negative sourdoughs. This difference persisted during the 6 days of storage, as you can see in this figure. This slide then summarizes the benefits of sourdough technology in wheat bread baking. The use of sourdough process is certainly one of the oldest biotechnological processes and has several benefits as seen in the blue box on the left-hand side. Sourdough technology can be further improved by EPS-producing lactic bacteria. The beneficial impacts include water absorption of dough, better dough machinability, retarded bread staling, increased loaf volume. Furthermore, due to mild acidity, larger amounts of sourdough can be used in baking without negative impact on flavor. I also want to mention here that EPS technology can be applied in various plant-based materials and suitable starters can be found for different food matrices. So let's move on and go to the second example. We are also well aware that lack of fiber and large offering of refined products with poor nutritional profiles are public health challenges worldwide. We are currently looking for new means to improve nutritional profile of food and beverage products. Consumption of foods rich in whole grains and cereal fiber has been shown to reduce risk for obesity, diabetes, inflammation, cardiovascular disease, and some types of cancer. Dietary fiber has well demonstrated health benefits and approved nutrition and health claims. The interest on high fiber unrefined healthy food is a consumer trend, and the need for natural fibers is expected to grow rapidly worldwide. Successful fiber ingredients should preferably be neutral tasting, light in color, and easy to adapt for various product categories. Cereal bran is one of the most common raw materials for increasing the level of dietary fiber in bakery products, but it often has negative influence on dough structure and sensory quality, thus limiting its use in bread baking. Brans used as such often gives a gritty texture, bitter and pungent flavor, and coarse mouthfeel. We have raised the question, could we modify bran properties with microbial fermentation in order to improve the functional properties? We have developed a biobran concept that combines mechanical processing of brans, hydrolytic enzymes, and microbial fermentation with lactic bacteria and yeast. Our studies revealed that bran bioprocessing is indeed an efficient and natural means to improve the palatability and processability of bran. I want to highlight here that processing temperature, time of fermentation, and starter microbes are all fundamental factors that will have an effect on the properties of the final product. With optimized process, we have obtained high fiber wheat bread with good textural and sensory properties. In addition to baking, fermented bran ingredients are also good in other food applications. For example, they can be applied in extruded products. And at this point, please allow me to welcome our food processing expert, Nestle, who will now continue with our case studies. Over to you, Nestle.
Thank you, Arja. I would like to first give an introduction very quickly to extrusion processing for those of you who are not familiar. Extrusion processing is a high-temperature, short-time process which is used to produce directly or indirectly expanded snacks as well as breakfast cereals. Expansion during extrusion processing is mainly starch-driven, and these products are generally rich in starch content and mainly consist from refined flour. High-fiber extrusion, mainly by use of insoluble fiber, such as bran, is challenging as it interferes with expansion of the product at the die exit. More than 10% of bran addition in the flour mix results in closed, dense structure, which will ultimately result in hard and non-crisp textures. In our case study, we modified rye bran with EPS-producing microorganisms and added 20 and 40% bran to rye flour. In this system, EPS-producing microorganisms yielded 5% extra production in situ. We compared the results with native bran added at the same level as fermented bran. We also looked at the effect of the extra addition externally. On the right-hand side, you see the pictures of control, native, and fermented bran snacks. As you would see, there is a clear impact already from these pictures, how fermentation of bran can have an effect on the expansion. In this figure, you are looking at cross-section images of extruded snacks. From left to right, endosperm rye flour without bran addition, 20% bran and 40% bran addition, where upper level shows native and lower level shows fermented bran. All images are taken at the same microscopic condition and has an identical scale. There is a clear effect of EPS bran addition on radial expansion of snacks. Fermentation of bran with EPS-producing microorganisms dramatically increased the expansion. An effect was also seen in the color of the snacks as fermentation of bran gave whiter bran color. We also looked at the textural properties by using a texture analyzer, and we have extracted hardness and crispness index values. For directly expanded extruded snack products, less hard, yet high in crisp textures are desirable. Fermentation of bran reduced hardness more than 50% of the control. However, exterior dextran addition had almost no effect. High crispness index, which you can see from the graph on your right-hand side, is an indicator of high crispness. Crispness index of fermented bran was the highest, where 40% bran addition had further boosted the crispness level. Again here, exterior dextran addition, which you can see from the pink bar, had no effect on crispness. We calculated the nutritional values of extrudates. To make high-fiber health claims in EU, there should be minimum 6 grams of fiber per 100 grams of product. Thus, additional 20 or 40% of fermented bran will allow to make you this claim without compromising the texture, structure, but also sensory properties. Bran is also rich in protein. Rye bran, for example, has 15 to 20% of protein, depending on the variety or the provider that you are working with. For source of protein claim, minimum 12% of the total energy should come from protein. Optimizing the recipe further might easily lead you to high in protein products if 20% of the total energy is provided by protein. I would like to now summarize the technological and sensory impacts of EPS fermentation of bran on extruded high fiber snacks. First, I want to point out extrusion with native bran has a limit of 10 to 15% bran addition, which will cause some degrees in expansion, increased hardness, reduced crispness, and yet in such a system, pure dextran addition will have no impact. However, extrusion with biobran you can go as high as 40% of bran addition, with improved expansion, less hardness, and even more crispy textures at 40% bran addition. Fermentation and in situ egg production will have a positive impact in this system. I want to now move forward with our next case, where we will see how fermentation could be utilized in protein-rich products. The global population is forecasted to increase to 7.6 to 10.6 billion people by 2050. This rapid growth, in combination with expected increase in welfare, will lead to an increased demand for animal protein, which is forecasted to increase by 52% until 2030. Thus, additional alternative and sustainable plant protein sources with high technological, sensory, and nutritional functionality are needed. Plant protein production requires less land and thus less source intensity than that of animal proteins, but plant proteins also pose challenges, especially when compared to the properties of the current animal proteins. I want to highlight that we have the drivers such as global protein supply security, restricted availability of animal proteins, the biggest important driver, consumer interest towards increased protein content in food. Thus, we need to have plant sources, and agro-side streams should be also utilized more efficiently and sustainably than before. However, this is quite challenging, as restricted protein availability within plant matrix needs to be sorted out, together with nutritional quality and anti-nutritional factors, not to mention the poor technological functionality. Also, I want to point out, United Nations decorates 2016 as the International Year of Pulses to raise the profile of pulses and to celebrate the role of beans, chickpeas, lentils, but also other pulses in feeding the world. Key actors involved in the production chain will communicate and contribute about pulses and how they benefit health, nutrition, and global sustainability. Faba bean, also known as field bean, broad bean, pork bean, or thick bean, is an annual legume growing in different climatic zones from Europe to Africa and Asia, where it represents one of the more ancient and common crops for food and feed. It has protein content which can go as high as 35% based on variety. They are also rich in vitamins, minerals, dietary fiber, but also bioactive compounds such as antioxidants, phenols, and gamma-aminobutyric acid. Yet, they are low in cost, being half of the price of soy and pea. They have milder bean taste compared to soy and suitable also for gluten-free products. Nevertheless, secondary metabolites may exert an anti-nutritional effect, which are also present, including pyridamine glycosides called lysine and promethine, condensed tannins, protease inhibitors, alkaloids, lectins, and many others. Their limitation is also due to bitterness, mainly coming from the tannins in the hull. However, dehulling prior to milling might significantly reduce this effect. Today, I'm going to present how you could modify the techno-functional and nutritional profile of faba beans by using fermentation toolbox. In our case study, we used Vicia faba minor, Conti variety, typical to Finland, which has a protein content of 35%. Release of proteins from the plant matrices are rather challenging, as they are in general entrapped within the plant cell walls. In these microscopy pictures, which you see on your left-hand side, red refers to protein and black is starch. On the image where you are looking at unfermented faba bean flour, you should be also able to see a light blue color, which shows the cell wall material. By fermentation, proteins are released from the cell wall matrix. The image on the bottom left-hand corner shows fermented faba flour with Lactobacillus plantarum. By fermentation, proteins are released from the cell wall matrix. The free amino acid in faba bean flour is 7 grams per kilogram flour, whereas fermentation increases this level more than double the amount, reaching as high as 16 grams per kilogram flour. We make high-protein, gluten-free faba bread where we use 70% faba flour. Fermentation of faba flour gave higher loaf volume with a more homogeneous structure and better texture. In the table, you see in vitro starch hydrolysis index for wheat, gluten-free faba, and gluten-free fermented faba bread. Fermentation significantly reduced the in vitro starch hydrolysis rate, which is also expected to reduce in vitro glycemic index. We also developed gluten-free faba pasta, which was based on 100% faba flour. A nice al dente texture is desirable among pasta consumers, which is typical to semolina pasta. In general, gluten-free pasta lacks this texture, naturally due to lack of gluten. We did texture profile analysis to optimum cooked pasta and found that gluten-free faba flour gave a nice texture where fermentation provided even higher hardness and chewiness values than the semolina pasta processed identically. High-protein gluten-free products are lacking where hybrid processing of faba beans in combination to fermentation can be utilized to design new ingredients and food products that can enter to the market. Reduction of anti-nutritional compounds, release of proteins and modification of amino acid profile are some of the benefits of faba bean fermentation. Fermentation is a simple and green process to modify the techno-functional and sensory properties of faba ingredients, but also other protein-rich ingredients. They provide also excellent nutritional and sensory profiles based on bread and pasta demos, which we showed you. My colleague, Dr. Arya Leitila, will now give a brief summary of today's webinar and provide you further information related to VTT's microbial food processing solution.
Okay, thank you, Nestle. I want to summarize this presentation with these take-home messages. Microbes are a key to produce new product innovations. They provide a natural production concepts and products with clean label image. We can use bioprocessing to improve properties of complex plant ingredients such as cereal brans. And microbes are also a tool to improve taste, nutritional profile, and functional properties of protein-rich products. I was really glad to notice a news at the Ingredients Network last week. Top food trends indicate that there will be a rise of fermented foods. Phil Lambert, who is also known as supermarket guru, predicted that already year 2015 will be the year of fermented foods. And I do hope that this will be an increasing trend also in the future. Now, before going into the question and answer session, I would like to give you some ideas how you could perhaps benefit from our microbial food processing solution. This slide shows you that there are several steps that need to be considered when designing a successful food fermentation concept. We can help you to build up a production concept from strain discovery and characterization into food and beverage applications. We have our own microbial bank, which was established already in 1959 as a collection of industrial brewers and bakers' yeast. Nowadays, the total holding of the collection is approximately 6,000 strains of bacteria, yeast, and filamentous fungi. Our international culture collection can be accessed from the following internet address. We also have to identify and characterize new bacteria and fungi. We also provide safe deposit agreements so that the industrially relevant and also patented microbial strains can be stored in a safe place. Our current research areas cover functional ingredients, fermented vegetables, baked products, snacks, and beverages. So you can meet us in several upcoming food and beverage meetings, for example, in the Global Food Technology and Innovation Summit held in London next March. Then we are present at the European Brewing Convention Congress in Porto in Portugal next May. You can also find a lot more information of us from our NutriTech platform, which can be accessed from nutritech.fi. And at this point, I will hand it over to our host, so Chance.
Thank you very much. So it's now time for today's poll question in our session. So please select the answer that is relevant to you and then press submit. So today's poll question is, which one of the cases presented did you find the most interesting? Your options are A, natural, B, high fibre, or C, protein rich. While you are voting in this poll question, I would just like to remind you that you can submit any questions that you have for our Q&A session by using the Q&A widget at the bottom of your screen or by using the questions box at the top left-hand corner of your screen. If you are watching this presentation on demand, you can still ask your questions even, and they will be forwarded to VTT. I would also like to encourage you to use the Twitter widget at the bottom of your screen to tweet about today's webinar. So I now believe that's enough time for the audience to have voted in this poll question. So I'm going to close the poll and move on to the results. Okay, so it seems that protein rich appears to be the most popular topic in today's session. Would you like to briefly comment on this before we move on to today's Q&A session?
Thank you very much for answering the poll question. It was really interesting to see the results, and thank you. Yes, protein-rich products are very important in the future. Or what do you think, Nestle?
Yeah, I was actually expecting this from the wall, so it were thanks for our attendees. So they have responded to my expectations related to the rising trend coming to the protein-rich utilization of plant proteins more as food ingredient or in food products. So it was nice to see that almost 50% of the waters went with the protein-rich case. Yep.
And then over to you, sir.
Thank you very much. So it's now time for our Q&A session for today. So please allow me to welcome Riikka Juvonen, Senior Scientist of Process Microbiology and Safety at VTT.
Thank you, Chance, for the presentation, and I want to welcome everybody here to this Q&A session on my behalf. So we have already got a lot of interesting questions here, and I think that we could start our Q&A session. So here we have the first question related to labeling of fermented products. So how are fermented products labeled? So I could actually provide the answer by myself to this product. So fermentation does not need any labeling, so it's a clean label technology when food-grade organisms are used to carry out the process. So you need to only label the ingredients that are used for the fermentation as substrate. So that was the first question, and then we have a second interesting question here related to the nutritional characteristics of fermented products. So what is the positive impact of a microorganism activity on product nutritional characteristics? So I could also comment on this question from my behalf. So yes, microbial fermentation has often a beneficial impact on nutritional quality of food products, and it can be tailored in that way that this impact can be increased and designed. So, for instance, as we have heard already today in our presentations, the fermentation can reduce the anti-nutritional factors, for instance, in various pulses. Microbial fermentation and activity can also release various bioactive compounds, such as phenolic compounds, and in that way increase the nutritional quality. Fermentation can also be used to enrich vitamins in situ, for instance, folate and B12 vitamin. The exopolysaccharides produced by microbes are often considered also as dietary fibers, and some of them are prebiotic compounds. So there are many different ways. So let's then move to our third question here, and that is then related to the equipment needed for the fermentation. So do we have any comments on this one?
Yeah, I can take that question. So you don't need to, obviously if you are doing fermentation in your factory, you don't need to do extra investments. But then if otherwise, what you would need is basically a fermenter tank, and then you need to also dry your material afterwards, depending on the application. If it's going to be a bread application, you don't need to dry it, but obviously if you want to do extrusion, then you have to first pre-dry the bran. So it is very much dependent on your process. Coming to the cost, half of the costs are coming from the raw material, roughly, and then also same amount from drying of the bran is also bringing some cost. So saying that, let's say that if the amount of your bran material is around 50 cents per kilogram, then it will bring its cost to a level of €1. But as I said, this is a very rough cost estimation.
Okay, thank you for Nestle. So then let's move on in the questions. So then we have here question related to our strains which we have been using, and that is that are they GMOs? No, these are all food grade organisms, and we have genetic modifications have not been used anyhow, so they are not GMOs. So then let me see. We have here a question related to benefits of exopolysaccharide fermentation compared to the use of purified exopolysaccharides. So would somebody like to comment on that?
I can comment on that one. First of all, as we have heard, ETS fermentation is a clean label alternative to purified hydrocolloid additives, so we don't have to label them in the products. And we are not using GMO organisms. Secondly, dextrans produced in situ in the food matrix can be more effective than just the pure hydrocolloids. And so we can say that fermentation is really a multifunctional technology, that you will get other benefits from microbial activity than just the production of exocellular polysaccharides.
All right. So we are getting more and more questions here. I try to keep on record. Okay, now again we have here one very nice one. So when you extract the amino acids from the cell wall, do you actually increase the amount of protein, or does it remain the same, but the amount of certain amino acids increases?
So I will take that question, Rika. So basically what I have showed you there was the free amino acids available. So you are not really touching the amount of protein, but you are increasing the amount of free amino acids. So you are increasing the availability of the protein, which is entrapped within the cell wall.
So, okay, yeah, thank you. Thank you, Nestle, for that answer. So then there is one question again related to exopolysaccharides and dextrane. So could you please comment how dextrane is formed in the sourdough?
Okay, I can take that one. Lacticus bacteria, and these are the cultures, they produce dextrans with an enzyme called dextrane sucrase. So they are producing that into the sourdough. And this enzyme catalyzes the formation of dextrans from sucrose present in the system. So unless flour with high, if we don't have flour with high endogenic content of sucrose, then we need a sucrose addition externally into the system. So Erika, do you have more comments on that one?
No, I think that was quite exhaustive and quite good one. No, I don't have anything to add. Yeah. Okay, then we could move on to questions related to plant proteins. So bitter taste is the key issue associated with plant proteins. So do we have a technology to remove this bitter taste to get a better flavor profile?
Okay, with the faba case, for example, first of all you have to understand where the bitter taste is coming from. So in our case study in fabas, the bitter taste was coming basically from the tannins which were in the hull. So simply by dehulling and fractionation, we were able to reduce the bitter taste significantly. So that could be one approach, but this is different from one case to the other.
So, and we know that the fermentation, if I may add to this a little bit, is normally also beneficial to the taste of different pulses. So normally fermentation is improving the taste of bean products and removing of some of the unpleasant notes. So continuing a little bit with the same topic, there is one question related specifically to our faba bean example. So do we have a data on the flavor characteristic changes of faba?
Yes, we have demonstrated, we have done flavor, but also we have done sensory profiling for the faba bread and also for the faba pasta, which we have showed you today. And obviously fermentation brings some sour taste, which is rather pleasant, particularly for bread. What you can also do when you have there some sourness engaged, you can also reduce the salt level in your bread. So that's also another benefit which fermentation brings. And it brings also, it's rather, how to say, the notes are rather neutral if you don't do fermentation, and with fermentation you are also bringing other flavor notes which are pleasant. Also same applies with the pasta. So both texture and flavor is pleasant.
Okay, yeah. Thank you, Nestle, for that answer. So we are approaching to the final questions. We may still have time for 2 questions here. So here it comes, now we go back to the exopolysaccharide fermentation, and there is a question related to mechanism of bran expansion. So how does fermentation of bran help expansion of extruded snacks? Do you have any comments on that?
So I take that answer, Rika. So we have a hypothesis there that by processing of bran with the producing microorganisms will promote the surface interaction of bran particles with the other biopolymers within the food matrix that would have an improved technological functionality. So that's why it's giving more expansion, because normally when you are doing extrusion with bran, as it's an insoluble particle, it interferes with the expansion as if it's acting like a needle at the dye exit, and then it restricts the expansion. However, with the producing microorganisms, they cover the bran, so that instead of interfering with the expansion, it is interacting with the other particles, other ingredients, or other biopolymers within the food matrix, so that it is contributing to the expansion.
Okay, thank you for a thorough answer. And now I think that we need to take our final question here, and that is related to other applications than we have here been showing to you. So there is a question about colored, natural colors. So do you have any solution for coloring products by using microbiological approach? I could maybe take that one myself. So we do have here at VTT quite many years studied Nordic berries and their use in food as ingredients, and we have been, by using microbial fermentation, we have been able to get new, nice, intense colors. So we have been, for instance, able to modify the lingonberry color and get, and we have a technology to extract these color substances from berries, and there could be some potential to use it as a natural colorant in food. So we do have solutions. Please contact us. So I think that I will now hand over back to our host, Charles, who can then finalize the webinar. Please, Charles, take over.
Thank you very much. If we didn't get round to answering your question in today's session, then your question along with your email address will be forwarded on to VTT, who will respond to you in due course. So before I conclude today's session, do any of our speakers have any final thoughts that they wish to leave with the audience?
Thank you, Chance. Hope our examples have shown you some possibilities of microbial food cultures, and we'd be happy to discuss with you also about several other options. And at this point, I want to warmly thank you very much for attending this webinar. And if you have any further questions, please do not hesitate to contact us. And at this point, I just want to say have a nice day or have a nice evening, and let's keep in contact. Thank you.
So that just leaves me to thank Aya, Nesli and Rika for what was a great presentation, and thanks to VTT for sponsoring today's session. To the attendees, a brief survey will appear on screen when this broadcast ends, and we would appreciate it if you took the time to fill this out. You will also receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. We look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned, and follow us on Twitter at BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. Thank you once again, and I hope you all have a nice day.